Yeah, talking about pronunciation, they made me observe that the rule I explained yesterday, well, was not quite the correct one, because C and G has a hard sound. Before consonant, but double consonants consonants count as one, like sorry, not hard, but so yeah. So this is still G and J. The G is a bit stronger, but that doesn't really matter. And Gn Li has a special pronunciation. This is N, this is Li, and not Gn and Gli, with exception. Here. But I'm not going. I don't want to go into that. So now back to Heegaard Floer homology. So today I'm supposed to construct the complexes, and it's a very long story, so it will be, of course, sketchy. So let's start from a sigma, alpha, beta, and z, a pointed Heegaard diagram. From this, we'll construct a complex Cf minus of sigma, alpha, beta, z, often abbreviated as Cf minus of alpha, beta, when sigma and z are clear from the context. And from this, all other one will follow by algebraic operations. Two standard assumptions on the Heegaard diagram. The first one, and this is really a standard assumption, I will never mention it again. Alpha and beta intersect transversely. And there are no triple intersections. This is, of course, a generic condition. It can be obtained by any very small perturbation of the alphas and the betas. A second assumption, this is, I will usually recall it, but maybe not always, but it should be there all the time, is something which is called weak admissibility. Which means that every periodic domain must have both positive and negative coefficients. For example, this diagram is not admissible. Because there is a periodic domain, which is this one, which has coefficient 1. So only a positive coefficient. So, and a fact in two parts. The first one will be in a very long but not so difficult exercise in the exercise sheet, is that every diagram, and when I say diagram, I usually mean a point Heegaard diagram, can be made admissible. By an isotopy of the alpha and beta curves. In fact, you can either move the alpha or the betas, but the proof is slightly easier if you allow yourself to move both. What? What do you mean? You know what a periodic domain is? So a periodic domain is a linear combination of elementary regions with certain properties. And the coefficients are the coefficients of the regions, of the elementary regions, which are in the sum. Then the other question is how you enumerate all periodic domains. I mean, it's not difficult. It's just boring. You sit down long enough and what?
I think that it would be useful to recall it with a higher degree.
Okay. Oh. A periodic domain is a linear combination of elementary regions and maybe I should recall what elementary region is. I don't go back to recalling what the Heegaard diagram is. That's, I give it for granted. Are connecting components, are closure of connecting components of sigma minus alpha union beta. Such that the boundary is a combination. Boundary of P is the periodic domain, is equal to a linear combination of alpha and beta curves. And the second is that the coefficient of the region with Z, so with the base point is 0. So usually to make a diagram admissible, you have to make it complicated in some good way. And another, I mean, if you were slightly more complicated but still kind of elementary fact, is that two weakly admissible Heegaard diagrams are connected by isotopy Handel slides and stabilizations through admissible diagram. So to define a topological invariant, it's enough to define Heegaard Floer homology for weakly admissible diagrams. Since this property is called weakly admissibility, you can imagine that there is a property which is called strong admissibility, which is a bit more complicated to both to state and to check. And it's needed to define HF minus, HF infinity without completing the ring of coefficients. However, there's not real gain of doing that, at least for the level of detail we're using here. So. Yes. In fact, the isotopies to make everything admissible is a bunch of winding along some curve. Those kind of isotopies are enough to make everything admissible. So now let's go one of the most important definitions, the Heegaard Floer generators. Is a G-tuple and in fact, it's actually unordered, like everything here is not really, both alpha curves, beta curves, I mean, we have to number them to give them a name, but it doesn't, the order doesn't really matter. Such that, so each of these points is an intersection point from an alpha curve and a beta curve. And each alpha curve and the beta curve has a unique intersection point on them. A quicker way to say is that xi belongs to alpha I intersect with beta sigma I for some sigma in the group of permutation over G elements. By the way, can you read the blackboard? Because here from close by, I see the writing of the previous talk. I don't know if it bothers you from far away or not. OK. Because for me, it's quite bothering. So Cf minus of this weakly admissible Heegaard diagram as a module is the free module over the power series ring on a variable u with coefficient in Z mod 2 generated by the Heegaard Floer generators. Well, actually, okay, so let's say the linear structure of the complex is fairly easy. I mean, these objects are easy to spot if you have a diagram. I mean, there might be a lot sometimes, but you sit down and you enumerate them with patience. It's not so difficult. The difficult part is the differential, which uses a weird construction. I mean, weird if you are not used to symplectic geometry, weird construction in complex analysis. So to do from that, it will be a long story. Let's start by well, maybe not to interrupt the flow of complicated stuff is going to come. We'll make still some topological preliminary. Let's take a region. So this is a linear combination of elementary regions. Then you can define, well, the boundary alpha of D is the portion of boundary D supported on alpha curves, and boundary B, D, the same thing but on beta curves. So what does it mean? I mean, D is a sum of elementary regions. The boundary D is a sum of segments over alpha and beta curves. Boundary alpha D takes only in the sum takes only those segments which are on some alpha curve, and boundary beta on the ones which are on some beta curve. And then we define pi2 of xy. This P is a historical reason. You will not understand why from this setting, and you shouldn't care. So we take two Heegaard Floer generators. We take P2 of xy is, I mean, there are several ways to define it, but for us, the quickest way is the set of regions such that the boundary alpha of D is equal to y minus x. So y minus x actually means, so the boundary alpha D is a sum of segments. So its boundary will be a sum of points. So this will be y1 plus dot 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 plus yg minus x1 minus dot 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 minus xg. And in a bit later, maybe it's mysterious now, but a bit later, it's you will understand what it means. Yeah.
Your alpha and beta were not oriented. However, you use the orientation of the surface to be oriented.
No, the alpha and the beta are not oriented canonically, but it's nobody forbids me to assign an orientation to them. And but I don't really need to. I don't really need to. Do I need to? Well, are cells in a cellular complex oriented? Because this is essentially a cellular complex, except that so you take your surface, you divide it with the alpha and the beta. if all regions were disks, that would be a cellular decomposition of your surface. And what we are doing would be cellular homology. Not all regions, not all elementary regions are disks, so it's not, I can't say what we are doing is a cellular homology, but from a combinatorial point of view, it doesn't make any difference. So it's, I don't know if it's necessary to be, them to be oriented or not. It's put the same condition you need to define cellular homology. That's the key point.
Maybe the alphas are not oriented, and you write delta alpha of V. That's oriented types. Oriented as boundary. That goes into the definition of periodic. So when you do this example, when you do in the results, this thing there, like where the thing is like diagonal. Why are we going to say that it has to be one times minus the other? Because orientations are used by the orientation of the regions, and they have to be fit together.
Anyway, I'm ready to bet 1 month of salary that you never ask yourself if cells are oriented when you study cellular homology. So I don't want you to ask the same question here. It's exactly the same thing. I mean, whenever you have a picture, you know what to do. That's the key point. And now we define a map I from P2 of xy to z. Let's call it a Lipshitz index. Because it was Robert who wrote down this explicit formula. And so this is I of d. I will write 2 things, and then I will explain you later what they mean. It's E of d plus nx of d plus ny of d. So I will tell you what these things are. E of d is what is called the Euler measure. So it's like the Euler characteristic, but it takes into account the fact that we have here we have something which is really doesn't have a smooth boundary. But it has a clear definition, which is the following. If d is equal to some ai di, where di are elementary regions, then E of di is equal to the Euler characteristic of di minus 1/4 the number of corners. Then we'll do at some point some explicit computations to understand. And then E of d is equal to the sum of ai E of di. Nx or nz are defined in an equivalent way, so I will only define nx. So nxd will be the sum over I of nxi of d. So I should tell you what it is. You have xi will be an intersection of an alpha and a beta curve, and you will divide locally the surface in 4 regions. And those will have coefficients a1, a2, a3, a4. And then nxi of d will be 1/4 a1 plus a2 plus a3 plus a4. And for y the same, you do it with y. But I mean, it's not, it's not so important the particular expression of this formula for what I'm going to say next, but just keep in mind that there is some formula that you can compute on a diagram, and it's not hard. Okay, now for the moment, let's stop with topology for the moment and go into complex analysis. Okay, first thing, we should fix an area form on omega. Oh, not on omega, an area form omega on sigma. Then we have an almost complex structure on sigma is a map, well, is an endomorphism J of the tangent bundle such that J square is minus the identity. So it's like a complex multiplication. And in fact, I mean, it's a difficult theorem that such a thing on a surface induces the structure of a Riemann surface. But on the other hand, it's very easy to see that once you have a Riemann surface, then you get something like that. Because, I mean, a Riemann surface is a complex manifold, so you have a complex structure on every tangent space. And that's the complex multiplication. So we say that J is compatible with omega if we take omega and we twist by J in the second coordinate, this becomes a Riemann metric. Then we take a path Jt for t in 0, 1, I mean a smooth path of almost complex structures compatible with omega. And from this, you can construct J, almost complex structure on R times 0, 1 times sigma by I. So by what? First of all, you show that you see that the tangent space of R times 0, 1 times sigma is isomorphic to the tangent space of R times 0, 1, which is C, I mean R2, because here we haven't put any complex structures there. So times the tangent space, the tangent bundle of sigma. So let's put this in some point. T of S TP. And then we define J so that on this space, J is equal to the usual complex multiplication on R2 that we identify with C2 plus JT, the almost complex structure we have chosen on J. So this is not a product almost complex structure because on the sigma component it depends on the point in the interval. So what we are doing, it's not exactly complex analysis, but still it's quite close. Yeah. Because it's an almost because it's I mean it acts separately on this and on that, and the square both here and there is minus the identity. So what? Big J is defined by this. This is the definition. Yes. Yeah. No, there's no obvious choice. It's, but the point is, the choice is not obvious, but possible choice live in a convex set. So in the end, it will really not, since the space of choice is contractible, in the end it will really not matter. But you need to, so it's important that all these J in this family are compatible with some area form. It doesn't really matter with which area form they're compatible.
So we start with the area form and then we fix everything.
Yeah. So a J-holomorphic Heegaard Floer curve is, this is a very long definition, so I'm sorry. It's F P JF U such that F, well, let's say FJF is a Riemann surface with boundary. And no boundary and no closed components. P is a tuple of marked point on the boundary. So half of those I declare them positive and half of those I declare them negative. And every component of the boundary of F has at least a positive mark point and a negative mark point. And positive and negative mark point alternate. So if you have some boundary component like this, you will have a positive one and then a negative, a positive and a negative, and so on. So it will be always even in a boundary component. On the other hand, numbering here doesn't really has much to do with the order on which they appear on the boundary. Then U is a map from F to R times 0, 1 times sigma, such that it's J-holomorphic, which means that du composed with Jf equal to big J composed with du. So if you put so enormous complex structure on a manifold makes its tangent bundle into a complex bundle. So and if you have a complex bundle, so we have a complex vector space. We can talk about the complex linear maps, and J-holomorphic means that the differential is a complex linear map with the complex structures on the tangent space defined by these two almost complex structures. So this looks innocent, but in fact it is a nonlinear partial differential equation. Another condition, and here, sorry, I have to read because it's fairly complicated, that the boundary of F minus, U is defined on F minus the set of marked points. The boundary of F minus the marked points maps to R times 0 times alpha union R times 1 times beta. The limit for Q that goes to Pi of PR composed with U of Q, and here it's Pi plus or minus is equal to plus or minus infinity, and that's what it means, the positive and negative punctures. So some notation that I forgot to introduce before. I'm sorry. is that we will have several projections from this space. We will have a projection to sigma that we will call P sigma. We will have a projection to R that we will call PR. And we will have also a projection to R times 0, 1, which we'll call PB, where B is as base. Okay. So here, PR composed with U is the R coordinate of the R component of U. The other condition is that the limit for Q that goes to Pi minus of P sigma composed with U of Q is equal to Xi. And the limit for Q that goes to Pi plus of P sigma composed with U Q is equal to Yi. This is a horrible definition. If I were good at drawing, I would try to draw a picture, but the picture need to be in a dimension 4, and I can barely draw in dimension 2. So it's I will not try. So 2U, we associate a region du, sometimes is called the shadow of U, as follows. We choose a base point, choose a point in each elementary region. And let's say we call the region with the base point D0, and we choose the base point in that region. And then we observe that R times 0, 1 times Zi is an enormous complex submanifold. Which means that it's J preserves its tangent space. And we define Nzi of U, the number of points count with the multiplicity of U minus 1 of this almost complex submanifold. So essentially, we intersect the image of U with that. So for the generic choice of Zi, this intersection is actually U is transverse to this, and we can actually count the number of points. however, we are in the almost complex world, and then you can count multiplicity of intersections, even if the intersections are not transverse, but that's a long story. And we will essentially not need that story. So let's pick Zi generic, and then really it's what you imagine. And then we define D of U as the sum of NZIU di. So, yes? What? I don't need it, and that's not true. At this point, it's not true. Essentially, this is more or less, this is the homology class that you get by mapping the fundamental class of F by U composed with a projection to sigma. That's morally speaking. A very easy lemma is that all the coefficients of du are non-negative, and they are all 0. Well, and at least one is, no, sorry, and they are all 0 if and only if U is a union or trivial strip. So I should define those, and let's take the first. We will do more examples of those curves, but so far the first example, which is trivial strips, we can take F have a disjoint union of G copies of R times 0, 1, and U of SITI. SITI are the coefficients of the ith copy of this disjoint union, is equal to SI TI XI. So this is a curve that is constant. I mean, this is a curve which projected to the base, projected to R times 1 is a trivial cover with G sheets, and projected to the surface, every sheet goes constantly on a Heegaard Floer generator. These are of course, the region of this the shadow of this gadget is trivial because, I mean, it misses the interior of every region. And what I'm claiming, it's not so hard to see that they are the only trivial ones. All the other ones have some coefficient which is strictly positive. So given x, y, Heegaard Floer generators, I define M of x, y is the set of holomorphic, J-holomorphic Heegaard Floer curves from X to Y. So, which means they satisfy all the properties that I've listed there. And we divide by reparameterizations of the domain. So if we have the orientation preserving diffeomorphism of the surface F, and we move and we transport the almost complex structure, the marked point with that diffeomorphism, we decompose U with that diffeomorphism, we essentially have done nothing. We don't want to count this as a different object, otherwise we'll have uncountably many. So for this reason, we divide by reparameterization of the domain. And then we decompose this into, so this object is called the moduli space, but we want to decompose it into different components where we have more control about on the topology of those curves. So we define mi equal to, let's say, I, and z equal to j, between x and y, the intersection, the elements of mxy with nz of u equal to j, and I of du equal to I. Okay, well, it's might not see a clear why, but the following theorem which is actually the difficult part of the story. Well, part of the difficult part of the story, not all the difficult part of the story, is that for a generic choice of JT, and I'm not going to specify what generic, I mean, generic means outside of a set of bare categories, first bare category. But I'm not going to say more than that. And for OJ, M I equal to 1 and Z is equal to J of XY is a smooth manifold of dimension 1. Every curve in it is an embedding. So here it comes the embedding. It's a consequence of this low index. It's not something that holds for every holomorphic curve. Are translations on sigma acts freely and transitively and the quotient. So translation, you know, since the almost complex structure we have defined on r times 0, 1 times sigma does not depend on the s coordinate. If we take a Heegaard Floer curve and we translate by changing its r coordinate, we still have an Heegaard Floer homomorphic curve. So, and the quotient m I equal to n and z equal to j xy divided by r is a finite set. Yes? No, z is an integer. It's not a multi-integer. When I write z, I write it mean the no. Z is always the base point in the Heegaard diagram, so it's one point, which is one of these zi. It's the first one of these I, but it's not. It's really just one. So this is a finite set. Okay, a few words here. Act sensitively here. What? Not one. It's freely, not transitively. Sorry. Yeah, that's freely. It's a bunch of points. I have never seen a situation where it's not one point. But also, the point is that the situation where you can actually compute the moduli spaces are very limited. So it's a few words, because taking a short break and because this is quite hard to digest. But we have chosen at the beginning an area form. Where do we use it? We use it to show that this is compact. The reason is having J adapted to an area form implies that the L2 norm of the gradient of U is bounded by the. I mean, it's equal to the integral of omega on U. And then weakly admissibility tells you that this integral is bound, that you can bound this integral, and then it's so you have a bound in the L2 norm of the gradient, and from that you run some bootstrap process and apply Elzel-Ascoli, and you get a compactness of the solutions. That's all I'm going to say about the analysis today. Don't do much computations on a diagram, but you understand that with this definition of the moduli space, you will never be able to figure out what a moduli space is concretely. But luckily, and that's what makes Heegaard Floer homology computable, is that if all coefficients of so let's put it like this. If we have some region from x to y with coefficients zero or one, we can use a split almost complex structure on R times 0, 1 times sigma four curves in with shadow D in the previous theorem. So this is a bit convoluted, but what I mean is, suppose you have some D, and let's say, suppose you have some D with index 1. And in the moduli space, look only at those curves which have whose shadow is that region D. And D has only coefficients 0 and 1. You could even weaken it a bit, but let's stay with that. Then the statement of the theorem that this portion of the moduli space is a smooth manifold and it's a fine number of points after the quotient, blah, 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 is true for the split almost complex structure. And provided that we choose the alpha and beta curves generically. But that's not something that costs much usually, unlike taking a generic almost complex structure that makes the equation more complicated. So in this lucky case, it's finding your element of the moduli space is equivalent to finding, in this lucky case, the projection to the composition of U with the projection to sigma or to R times 0, 1 are both holomorphic. So in this case, understand your moduli space is equivalent to finding two holomorphic maps in dimension 1, and that often a manageable thing. And then, of course, this property applies only for some specific curves and might not. The split almost complex structure might not be good enough to compute the other moduli spaces. But that's not a problem, because once we have found how many curves there are in this case for the almost complex for the split almost complex structure, we can take a generic, very small version of it, and we will go back in the setting of the original theorem, and the number of curves we have found here will not change if you do a small change. So this is that allows us to make a lot of computations actually in Heegaard Floer homology. And so then what I'm going to do now is, well, first I've done all this stuff and I will define the chain complexes. And then I will do some examples so that you can get a feeling of how the things work. Yeah. What? Split almost complex structure means that it's a remember we had a family depending on T in the region. It means that the family is constant in T. Yes. So we take a Heegaard Floer generator. I want to define what is boundary minus of x. And so we want to define the boundary minus, which is the boundary between CF minus alpha beta to CF minus alpha beta. So now we define it. This will be a sum over all y other generator. Will be a sum over j, a natural number. For me, natural number includes 0. Of the number of points in M I equal to 1 and z equal to j of xy divided by r. I remind you that this we have seen in a finite number, a finite set, so we can count it, times uj times y. On the other hand, there's no guarantee that we get a finite sum. This could be non-empty. I don't know any explicit example, so I don't know if this is possible, but in principle, it's possible that there are only infinitely many things which are that this sum is really infinite. So we really we need to complete. And we will see that even if at this stage I don't know any example when you to complete, at further stages, which we're not going to that detail, but when you prove invariance, there is really a need to complete here. Otherwise, things can go very wrong. This is somewhat the master complex. All other three can be recovered from this by some algebraic operation. So first is CF hat of sigma alpha beta z. This is CF minus of sigma alpha beta z tensor over this fu with f, the field on which u acts trivially. On the other hand, this has a nice description, so it's worth writing down it explicitly. So CF hat of sigma alpha beta z is generated over the field by Heegaard Floer generators, and the boundary essentially the boundary uses only curves that don't pass through the base point. So boundary hat of x is equal to the sum over all y of the number of points in the moduli space of index 1 and nz equal to 0 from x to y times y. Then CF infinity of sigma alpha beta z is by definition CF minus tensor over fu of the Laurent series with the ring of the Laurent series. Well, we complete only on the positive side, not on the negative side. No. Yes. And then we have CF plus is equal to CF minus a tensor over the power series with the quotient ring of this divided by u times the ideal of power series which has only exponents which are strictly positive. So from this, you can see if you look at a bit carefully on what this means, this form you can see that for every element let's say A in CF plus, there exists n such that UNA is equal to 0. So this is a property I forgot to say yesterday and was necessary to do the first two exercises on my exercise sheet. Yeah? Where? No, I cannot. This is an FU. I've never said that CF plus is a module over the polynomial of the Laurent polynomial. CF plus is a module only over the power series ring. And in fact, it's even, since the action U is somewhat nilpotent, it's not strictly speaking nilpotent because the n depends on this element. But on every finite set it's nilpotent. Then this follows that actually you can see this as a FU module. It's not, there's no need to complete here. And if you go on if you use the classification theorem of modules over the polynomial ring, you will see that CF plus, HF plus, all these actions of U are read in every by the homology. And HF plus is of the form, there will be a certain number of infinite towers plus a certain number of finite towers where you have U that goes down and eventually goes to 0. What? Here? No.
I think that you have to see this as just the F bracket module.
Yeah, exactly. It's isomorphic to that. It's isomorphic to that as an FU module.
And whether you put the U there or not, it does not matter.
Yeah, I put U here. It does not matter at this point. I put U here because I want if I manage to talk about degrees, and Marco Golla will surely have to talk about degrees, I want the degrees to match the original definition of Ozsváth and Szabó. It's because Yeah. Ozsváth and Szabó did, which is not exactly this, but it's equivalent to this, so I have to put this U here. Otherwise, everything I get here, all degrees I would get here would be off by 2 with all degrees that Marco Golla will use next week, and that's something I do not want. I have up to what moment, up to what time? What? Okay, so I should more or less finish. Okay, let's do some examples. I mean, not yet of computing Heegaard Floer homologies, but of at least of moduli spaces. And the first example, I mean, which is somewhat the base of everything, remarkably, I mean, is the following. So you have a region like this. D is a region. So find all Heegaard Floer maps with this shadow. Okay. And let's here X, and let's here Y. So there could be some, I mean, this is a piece of a diagram. It could be a piece of a big diagram. There could be other coordinates, but they have to be the same for the two components. So big X and Y differ only at those two coordinates. All the other ones are the same, and we don't care about the other ones. So let's focus on this. First of all, we compute the index. So remember, it's ED plus NXD plus NYD. So what is ED? So this is also an elementary region, so there is not much to do. It is the Euler characteristic of D minus 1/4 the number of is 1/4. ED is equal Euler characteristic of D minus 1/4 the number of corners. This is 1 minus 2/4. There are 2 corners equal 1/2. And then ND and NY are the average of the multiplicities of the 4 regions next to a crossing. So the multiplicities are 1, 0, 0, 0, 1, 0, 0, 0, 0. So the average are 1/4 and 1/4. So this is equal to 1/2 plus 1/4 plus 1/4 is equal to 1. So the index is the good one. Now let's see what we can do. So let's pretend this is a genus 1 diagram and we have only this, this condition. Now it comes to the big hero of the theory, which is the Riemann mapping theorem. The Riemann mapping theorem says that it's if you have a simply connected subset, open subset of C, which is not all C, it's biomorphic to the disk. And moreover, this is usually not taught in the elementary courses, if the boundary is good enough, this biomorphism extends smoothly to the boundary. Or at least continuously, but I mean, anyway, it's extended with good regularity to the boundary. Then we apply this to this portion of plane given by D, and we found a holomorphic map called U sigma. Okay, first of all, I should observe D is here we have a region where all coefficients are 1 and 0. So all coefficients equal to 1 and 0 implies that we can compute the moduli space by using the split almost complex structure, which means that the composition of U with the projection to sigma and to the projection to R times minus 1 will be both holomorphic. So what we are actually looking at is a pair of holomorphic maps. So we have a holomorphic map U sigma from R times 0, 1 to sigma which covers D. And how we define U? Well, we can define U from R times 0, 1 to R times 0, 1 times sigma by U of ST equal to ST U sigma of ST. So this is clearly a Heegaard Floer holomorphic map. And then what do we holomorphic map, this one covering D. So in particular we want that U sigma goes to X as S goes to minus infinity, and U sigma go to Y as S goes to plus infinity. Now, how many of these maps we have? So moreover, by Riemann mapping theorem, so we imagine we have U sigma and V sigma doing the job. Then we know that, we applied the Riemann mapping theorem. So we know that U sigma and V sigma, at least U sigma that we found by Riemann mapping theorem, the other one maybe we don't, is a biholomorphism. So we can invert it. So we consider U sigma U sigma minus 1 composed with V sigma goes from R times 0, 1 to itself, is holomorphic, maps R times 0 to R times 0 and R times 1 to R times 1, and okay. And let's say maps minus infinity to minus infinity, and plus or minus infinity to plus or minus infinity. So this implies, from some elementary almost complex analysis, which I'm not able to do at the blackboard, but you look at the automorphism of the disk and you see that. This implies that U minus 1 sigma composed with V sigma is a translation. So it turns out that every map covering D are of the form ST that goes to S plus A T U of S plus BT. S plus B, comma T. So translations at the source and at the target. However, remember that we were dividing by automorphism of the source. So we can choose to put this to 0, and it remains automorphism of the target, and we had to, but we also had to quotient by that, so it's that also goes away, and we have a unique thing remaining. So the subset of, let's call MD, is as the, I mean, MD divided by R, which is, okay, sorry, let's call MD the set of U in MXY such that D of U is equal to D. Have that MD divided by R has a unique point. Yeah, I mean, I will do the next example next time.